DNA allows this construct to be taken up by cells. So this is really, again, counterintuitive. Even though linear DNA doesn't get taken up by cells, we have found that these structures, which have dense layer of DNA on it, which are much larger than linear DNA, can get taken up by cells very easily. And you can also use the recognition properties of the DNA to detect different molecules. And importantly, this dense arrangement of the DNA imparts resistance to the nucleases that I talked about in the previous slide. So the enzymes that chop up DNA, turns out it prevents this structure from getting degraded as fast. And it also prevents the protein from getting degraded by proteases. And if I were to look at the protein core now, that allows you to look at structures based on protein-based recognition. And because we know that proteins are very, very specific for their analytes, like enzymes have very high specificity for their substrates. So that allows you to look at your target analytes with very, very high specificity. And the surface of a protein is heterogeneous, right? We have many different residues on the surface. So this allows you to modify or attach DNA sequences on the surface of the protein in a site-specific manner. This is something you cannot really do with an inorganic nanoparticle by like gold, because you can't really control where on the nanoparticle your DNA attaches. Using a protein, you can control that. All right, so now I'm going to show you two examples, one in which we use the DNA as the recognition element, and the other where we use the protein as a recognition element. So DNA can bind to molecules, but we want to have a signal that tells us that this binding has happened. And to do this, what we did was we developed a new strategy called forced intercalation aptamers. So there are these classes of dyes. These dyes, when you excite them with light, they undergo intramolecular rotations, and therefore they're non-fluorescent. But if you restrict their rotation, then they fluoresce. So if I were to have a DNA sequence and I replace one of the bases in my DNA sequence with this dye, when my DNA sequence binds to whatever molecule or target I'm interested in, if the DNA changes its conformation such that the dye is forced to intercalate or fit between the DNA base pairs, it's not going to be able to rotate, and therefore its fluorescence is going to be turned on. So in this way, we can detect whatever target molecule we're interested in. So in this example, we were looking at protons. So we made this protein-based spherical nucleic acid with a protein as the core and a DNA shell that changes its conformation when you decrease the pH and turns on its fluorescence. So what you see is when you decrease the pH, you do see about 9-fold increase in fluorescence because of the formation of this structure and the turn on of fluorescence of this dye. And now if I were to treat cells with these constructs, we can then analyze the cells. So we can analyze these cells one single cell at a time, but we can analyze thousands of cells using a technique called flow cytometry. And then if we were to look at the data, what we see is you see that cells that are at a pH of 5 are about twice as fluorescent as cells that are clamped at a higher pH, like 7.5. So next we wanted to look at whether we can make constructs where the protein acts as the recognition sequence. So we used glucose oxidase as the protein core in this case, and we developed a new two-step assay. So in this assay, what happens is we know that glucose oxidase catalyzes the conversion of glucose to gluconic acid and forms hydrogen peroxide. So if we were to use a dye that reacts with hydrogen peroxide and produces a fluorescent molecule like fluorescein, then we would be able to detect the hydrogen peroxide, which is basically coming from glucose. So now we can detect intracellular glucose levels using these glucose oxidase spherical nucleic acids. All right, so if I wanted to just do this in a test tube, what I see is that if I add different amounts of glucose in the presence of dye and the glucose oxidase spherical nucleic acid, my fluorescence increases as I have more and more glucose. And this is very, very selective for glucose in the presence of other molecules or other sugars that look like glucose but are not really glucose. And finally, if I were to treat cells using these constructs, we see that when you treat the cell with glucose oxidase spherical nucleic acids, you see a lot more fluorescence compared to cells that are treated with the dye alone, telling you that you really are detecting intracellular glucose levels. So we tested this in 9 different cell lines, representing a mix of different cancer cells, normal cells, adherent cells, suspension cells. And in all of these cases, we were able to detect intracellular glucose levels. All right, So what does this really mean? Like, what is the consequence of having structures like this? Well, the consequence is it can really enable new technologies. For example, it can help us to detect and isolate circuit metastasis early.